The Cambrian Explosion had faded, but its impact still echoed through every ocean on Earth. The world was no longer a place of scattered experiments in life. It was a world filling, changing, accelerating. 40 million years had passed since the first great burst of creativity and evolution, and now the stage was set for something even larger, the complete transformation of Earth's oceans into bustling ecosystems. More crowded and complex than anything the planet had seen before, the Ordovician period began quietly. No dramatic eruptions, no sudden shift in climate, just a gradual reshaping of the continents and seas. Most of the land was gathered near the equator, forming small continents surrounded by vast, warm oceans. And those oceans were the perfect cradle for life. Shallow, sunlit seafloors stretched for thousands of kilometers, creating huge marine habitats where evolution flourished. The first big change was stability. The early Cambrian world had been chaotic, filled with predators discovering new ways to hunt and prey discovering new ways to survive. But now, life settled into rhythm. Instead of constantly reacting to new threats, organisms began to specialize, refine, and expand. Diversity didn't just increase, it exploded again, creating one of the greatest surges of life in Earth's history, the Great Ordovician Biodiversification Event. Trilobites, once dominant, were now only one part of a growing cast. New species emerged that took advantage of nearly every possible ecological niche. Some trilobites became burrowers, hiding in the seafloor. Others evolved spines and armor to defend against predators. Their variety was enormous, and the Ordovician seas became home to hundreds of distinct forms, each perfectly adapted to its place in the environment. But trilobites were no longer the stars. New creatures rose to prominence, reshaping ocean ecosystems. Brachiopods, shell-bearing animals that resembled clams, spread across the seafloor, forming dense, carpet-like communities. Graptolites, drifting colonies of tiny organisms, floated through the ocean like dark ribbons, leaving fossil trails that would later help scientists map time itself. Then came the giants. Nautiloid cephalopods evolved long, straight shells that could reach several meters in length. These were the first truly large predators on Earth. Streamlined hunters equipped with jet propulsion and sharp tentacles. For the first time in history, the ocean had apex killers that patrolled the deep like underwater spears. At the same time, early jawless fish began to appear. Small, armored, and primitive, they were nothing like modern fish, but they represented a turning point in evolution. For the first time, vertebrates, animals with backbones, entered the scene. They were tiny players in this ancient world, but they were the ancestors of everything from sharks to dinosaurs to humans. Reefs also began to rise. Unlike Cambrian reefs, which were fragile and patchy, Ordovician reefs became massive structures built by coral-like organisms called bryozoans and sponges. These reefs stretched across coastlines, creating complex habitats that supported thousands of species. They were ecosystems within ecosystems, teeming with life, shelter, and competition. And above all of this, the climate remained warm and stable. Sea levels were high, the continents were small, and Earth, for a moment, seemed like a perfect world for life to grow without restraint. But stability never lasts forever. The seeds of catastrophe were already being sown. Far away, in the shifting movements of continents and the silent buildup of ice that would one day change everything. The Ordovician had begun in calm seas, but it would end in one of the greatest mass extinctions the planet had ever known. As life continued to expand across the Ordovician oceans, evolution grew bolder. Every shallow sea became an arena of experimentation. New body shapes, new strategies for eating, mating, swimming, and surviving. The biodiversity of this era didn't just increase in number, it transformed in complexity. Entire ecosystems that had been impossible in the Cambrian now emerged fully established. One of the greatest innovations of the Ordovician was ecological layering. Instead of most organisms living on or near the seafloor, the ocean split into distinct vertical zones. Floating creatures dominated the surface waters. Drifting colonies thrived in the mid-depths. Predators stalked the open water. and bottom dwellers formed dense communities far below. This vertical complexity allowed more species to coexist without directly competing, creating a biological high-rise structure unlike anything seen before. Plankton, small and nearly invisible, became some of the most influential organisms on Earth. Their sheer abundance created the foundation of the marine food chain. Graptolites, in particular, flourished. They hung suspended in the water in long, zigzagging colonies, drifting with the currents like living filaments. Their global spread makes them one of the most important fossils for dating this period. Each species marks a specific slice of geological time, like timestamps frozen in rock. ... Meanwhile, on the seafloor, brachiopods and bryozoans expanded into vast beds that covered entire regions. They built tiny, interconnected colonies that filtered nutrients from the water. These organisms were so successful that they would remain among the dominant marine life forms for the next 300 million years. With food sources becoming more abundant, predators evolved sharper tools. Nautiloid cephalopods reached their peak. Some species grew over 5 meters long, their straight shells gleaming like polished stone. They propelled themselves using jets of water, maneuvering with surprising agility for animals encased in rigid armor. They were the top hunters of their time, the sharks of the Paleozoic. Among the more curious inhabitants of the Ordovician seas were early echinoderms, ancestors of starfish, sea urchins, and crinoids. Crinoids, often called sea lilies, anchored themselves to the seafloor and stretched their feather-like arms upward to catch drifting food. In massive numbers, they created underwater meadows that swayed gently with the currents. Some regions became so thick with crinoids that when they died, their skeletal remains piled up into entire limestone deposits that still exist today. But one of the quietest developments would become one of the most important: the rise of early fish. Ostracoderms, the first vertebrates, were small, jawless creatures covered in armored plates. They lacked the speed of modern fish, but they had new advantages: internal skeletons, more advanced sensory systems, and the beginnings of true swimming control. With vertebrates now in the oceans, evolution had opened a pathway that would eventually lead to mammals, reptiles, birds, and humans. Throughout all this explosive diversification, Earth's climate remained warm. In fact, the Ordovician is one of the warmest times in the last 500 million years. The poles were nearly ice-free, sea levels were hundreds of meters higher than today, and shallow continental seas covered much of the land. These warm waters allowed the expansion of reefs, plankton, and marine habitats on a global scale. Yet beneath this apparent paradise, subtle changes were beginning to unfold. Shifts in ocean chemistry hinted at future instability. Volcanic eruptions released bursts of carbon dioxide into the atmosphere. The continents slowly drifted toward new positions, altering ocean currents. Plants, still microscopic and limited, began to spread onto land in small patches, quietly transforming the atmosphere piece by piece. Each of these changes was minor on its own, but together, they set the stage for one of Earth's most dramatic climate collapses. For now, though, the Ordovician remained a thriving world, a planet ruled by oceans, illuminated by sunlight, and filled with life, more diverse than anything seen before. As the Ordovician period progressed, Earth's oceans became more dynamic, more crowded, and far more competitive. Life had reached a point where simple existence was no longer enough. Species began adapting not only to survive, but to outmaneuver one another. Every ecosystem, from the shallowest tide pools to the deepest continental shelves, turned into a stage for evolutionary invention. Reefs grew into architectural masterpieces, built slowly, piece by piece. By corals and sponges, they expanded into sprawling underwater cities. Caverns, ridges, tunnels, crevices, and towering coral walls created a labyrinth of habitats. Countless creatures hid in the shadows, grazed along the surfaces, or drifted above these structures. These reefs were some of the earliest examples of true ecological complexity, webs of life so interconnected that removing even one species could shift the balance. Brachiopods carpeted the seafloor in numbers almost unimaginable by modern standards. Shells lay packed together like fields of pebbles, stretching out for kilometers. Each species settled into its own niche, Some clung to rocky outcrops, others burrowed halfway into the sediment, and many formed dense, layered mats. Their filter-feeding activity helped cycle nutrients throughout the water, stabilizing entire marine ecosystems. Bryozoans, tiny colonial animals, expanded into intricate lace-like structures, each colony acting almost like a single organism. They built delicate branching forms that resembled frozen coral snowflakes. Many species anchored themselves to seaweeds or shells, creating miniature forests that swayed in the currents. The level of cooperation within these colonies foreshadowed the highly organized societies that would appear millions of years later. Meanwhile, the midwater realm, the open ocean between the surface and the seafloor, filled with drifting life. Graptolites reached their evolutionary height, forming complex, interconnected colonies that floated through the water like living threads of ink. Some dangled in single chains, others branched like abstract scribbles. They rose and fell with ocean currents, forming vast clouds of drifting organisms that stretched for hundreds of kilometers. This made them one of the most abundant and widespread forms of life on the planet. In these rich waters, predators became more varied and more specialized. Nautiloid cephalopods were still the apex hunters, but even they evolved into new shapes and sizes. Some species developed shorter, curved shells that allowed tighter turning. Others grew longer and heavier, becoming slow-moving ambush predators that drifted above the sea floor, waiting for movement below. Arthropods, with their enormous diversity, continued to dominate the Ordovician seas. Trilobites, although no longer the rulers they once were, still existed in astonishing variety. Some developed spines for protection, others flattened themselves to glide across the sediment, and a few even evolved large compound eyes to detect the faintest movement. Their adaptability ensured their survival through countless changing environments. Then there were the eurypterids, early sea scorpions, which began their first steps toward dominance. These creatures, precursors to some of the largest arthropods in history, were already formidable in the Ordovician. Most were small, but fast and agile, using their flattened bodies to paddle through the water. Their claws were efficient tools for seizing prey, and their simple but effective eyes made them alert hunters. In the coming periods, they would become giants, but here they existed as swift predatory shadows. And yet, among all these remarkable organisms, the most revolutionary players were still the small, armored fishes, the ostracoderms. Though jawless and slow, their internal skeletons and protective plating gave them a resilience unmatched by most invertebrates. Their bodies hinted at a future where speed, agility, and predation would rise to new levels, but for now, they remained quiet participants in a world still ruled by invertebrate life. The continents continued their slow drift. Gondwana moved steadily toward the South Pole, creating enormous climate contrasts across the planet. Tropical regions remained warm and teeming with life, while southern areas cooled, forming environments that would soon play a crucial role in Earth's changing climate. On land, life remained mostly microscopic. Thin bacterial crusts clung to damp surfaces. Early moss-like plants began to gain a foothold along riverbanks and coastal areas, capturing carbon dioxide and releasing oxygen with increasing efficiency. These early photosynthesizers were tiny, fragile, and limited, but their impact on the atmosphere was growing. Small changes in carbon dioxide levels might seem insignificant, but over millions of years, they shifted the planet's temperature in ways that could not be ignored. Through all this, the Ordovician world thrived. It was a time of diversity, abundance, and ecological innovation. Evolution seemed unstoppable, pushing life into every available niche, filling the oceans with forms both familiar and alien. But beneath the prosperity, the first signs of danger continued to intensify. Ocean chemistry shifted again. Volcanic activity increased in several regions. Carbon dioxide levels fluctuated unpredictably. Continental movement altered the flow of warm and cold currents. The Ordovician was reaching a tipping point, a moment where Earth's natural systems could no longer stabilize themselves. A cascade of environmental changes was building in the background, silent and unstoppable. Soon, the world would face one of the most dramatic collapses in its history. As the Ordovician period approached its later stages, the world beneath the waves grew even more complex. The oceans teemed with life at every level, from microscopic plankton to towering cephalopods. Entire food webs now existed that would have been impossible only tens of millions of years earlier. But with complexity came vulnerability, and Earth was beginning to shift into a state of profound instability. The first hints of trouble were almost invisible. Subtle changes in the ratio of oxygen and carbon in the oceans pointed toward shifting temperatures. Certain species of plankton began to decline while others surged. Though tiny, these organisms were the engines of marine productivity. Their rise or fall could spell the difference between flourishing ecosystems and collapsing ones. Gondwana's slow drift toward the South Pole continued, and as the continent inched into colder latitudes, it brought dramatic changes not only to the land but to the sea. Coastal waters cooled, altering the habitats of countless marine creatures. The once warm shallows, ideal for reefs and filter feeders, now fluctuated between seasons of warmth, chill, and instability. Large cephalopods, once dominant everywhere, began to retreat from certain regions. Some species grew smaller, others shifted toward deeper water. They were not disappearing, not yet, but the signs of ecological stress could no longer be ignored. Meanwhile, another force was reshaping the atmosphere: the gradual expansion of early land plants. Though still limited in size and diversity, these primitive pioneers captured carbon dioxide from the air more efficiently than their microbial predecessors. Over millions of years, their slow, persistent activity lowered atmospheric CO2 levels. What began as a subtle influence grew into a major climatic force. As carbon dioxide declined, global temperatures began to fall. At first, the cooling seemed ordinary, the natural rhythms of a dynamic planet. But soon, the temperature drop accelerated far beyond normal patterns. Seasonal ice began to appear around the edges of the South Pole. Snow fell more frequently. Winters grew longer. The world was transitioning from a greenhouse Earth to an icehouse Earth. In the oceans, cooling waters triggered a chain reaction. Warm water species began to migrate toward the equator. Coral reefs shrank in size. Bryozoan forests and crinoid meadows thinned. Even the enormous brachiopod beds, once stretching across thousands of kilometers, began to show gaps. The midwater world changed as well. Praptolites, which had once formed vast drifting clouds, saw major shifts in their distribution. Some species vanished completely. Others expanded into new territories, following the altered currents and temperature zones. These changes weren't random. They were the early signals of a world under stress. For the first time in tens of millions of years, extinction rates exceeded speciation rates. Still, the oceans continue to support an extraordinary diversity of life. Predator-prey relationships remained strong, and many regions were still abundant with organisms. But evolution could not keep pace with the rapid environmental changes spreading across the globe. Then came the moment that changed everything: the formation of massive ice sheets on Gondwana. As temperatures dropped further, snow no longer melted in the southern highlands. Year after year, layer after layer accumulated, compressing into thick glacial ice. These ice sheets expanded outward, reflecting more sunlight into space and accelerating the cooling cycle. As water froze into ice, global sea levels plummeted. Entire continental shelves, the shallow, fertile regions that had supported most Ordovician life, were exposed. Coastal ecosystems collapsed almost overnight. Reefs died as they were left stranded above water. Countless species that depended on shallow seas lost their habitats entirely. The deep ocean, once buffered from surface changes, began to feel the effects as well. Cold, dense water sank rapidly, altering circulation patterns. Nutrient-rich currents weakened. Oxygen levels fluctuated dangerously. The delicate balance that had allowed Ordovician biodiversity to flourish was unraveling. In these harsh new conditions, predators suffered the most. Large cephalopods found their hunting grounds fragmented and unstable. Trilobites, despite their adaptability, experienced wave after wave of population decline. Even the resilient ostracoderm fish struggled as food webs collapsed around them. The crisis deepened as the glacial expansion reached its peak. Temperatures plunged to some of the lowest levels in 500 million years. Entire ecosystems vanished. Species that had dominated for millions of years disappeared with shocking speed. The Ordovician Silurian extinction had begun, one of the most severe mass extinctions in Earth's history. Yet even as the planet froze, pockets of life survived. In deeper, more stable regions of the oceans, small communities found refuge. Some species adapted to the cold, others endured simply because their environments remained insulated from the chaos above. Evolution had pushed life to extraordinary heights during the Ordovician. Now, the planet was testing the limits of its resilience. The end was near, but so was a new beginning. The final chapters of the Ordovician period unfolded with a stark, unforgiving intensity. What had once been a world of warm, fertile seas now stood on the edge of environmental collapse. The ice sheets that grew across Gondwana were not temporary visitors. They were architects of a global transformation. Their expansion reshaped coastlines, altered ocean circulation, and drained the shallow seas that had nurtured the planet's greatest early explosion of biodiversity. As sea levels continued to fall, entire habitats disappeared beneath the advancing land. Coral reefs that had flourished for millions of years were left stranded above water, bleaching in the sun and drying into brittle skeletons. Sheltered bays and coastal platforms turned into deserts of exposed sediment. Creatures adapted to narrow ecological boundaries, specific temperatures, precise depths, predictable currents, suddenly found themselves displaced or stranded. The collapse was not uniform. In some regions, the shift was gradual. In others, it was catastrophic. Species that depended on stable warmth suffered the most. Trilobites, once among the most versatile and successful organisms on Earth, saw vast declines. Many lineages disappeared forever. Bryozoans and brachiopods, creatures that had dominated the seafloor, endured heavy losses as their feeding strategies failed in colder, less nutrient-rich waters. Graptolites faced one of the most dramatic declines. Their drifting colonies, once so widespread and abundant that they served as precise markers of geological time, dwindled to a fraction of their former diversity. Entire species vanished from the fossil record as shifting currents and cooling waters disrupted their life cycles. Even the great cephalopods, the apex predators of the Paleozoic seas, struggled against the changing environment. Their once dominant presence faded as food webs collapsed, prey species disappeared, and cold temperatures hindered their metabolic efficiency. Some adapted by moving into deeper waters, but many could not adjust in time. As glacial activity reached its peak, the Earth entered one of its coldest eras of the Phanerozoic. Massive ice sheets locked away vast amounts of water, driving sea levels downward by as much as 100 meters. The exposed continental shelves. The cradle of Ordovician life dried into barren expanses. With each meter the sea retreated, another layer of marine community was erased. Yet, even in this seemingly desperate world, evolution continued its silent work. Species capable of tolerating colder, deeper environments persisted. Small, hardy organisms held on in regions where conditions remained relatively stable. These survivors, often overlooked in the grand narrative of evolution, would become the ancestors of future lineages that flourished once the crisis had passed. The Ordovician Silurian extinction did not unfold in a single, devastating moment. Instead, it came in waves. The first wave struck as glaciation expanded, cooling the planet and draining the seas. The second wave followed when the glaciers began to melt. As temperatures warmed and sea levels rose once more, the oceans experienced rapid, chaotic changes. Low oxygen conditions spread through many regions. Nutrient cycles destabilized. Species that had endured the cold now faced a new and equally deadly challenge. A world recovering too quickly for stable ecosystems to reestablish themselves. It was this 1-2 punch, this cycle of freezing and flooding, that resulted in the loss of nearly 85% of marine species, Whole families of organisms, which had thrived for tens of millions of years, vanished. It was one of the greatest biological turnovers in the history of the planet. And yet, mass extinction is never just an ending. It is a reset, a restructuring of evolutionary possibilities. When the ice sheets finally receded and temperatures slowly stabilized, the seas began to refill. New coastlines formed, new shallow environments emerged. The oceans, though quieter and emptier, were ready to be repopulated. In these calmer post-extinction waters, the survivors began to diversify. Small fish ventured into new territories. Resilient brachiopods and corals returned to abandoned ecosystems. Primitive plants on land continued to spread, paving the way for terrestrial colonization that would eventually reshape Earth forever. The Ordovician had begun as an age of warm seas, ecological innovation, and incredible biodiversity. It ended as a world transformed, colder, sharper, and permanently altered by the forces of ice and climate. But the devastation it brought cleared the stage for new evolutionary developments. A new era was beginning, one that would see ecosystems rebuilt from the remnants of catastrophe. The Silurian period awaited, a world of recovery, renewal, and the next great steps in the story of life. When the glaciers finally retreated and the sea began its slow return, the world did not simply go back to what it had been. The Ordovician seas that came into being after the ice were new in nearly every way. Chemistry altered, coastlines redrawn, nutrient cycles rebalanced, and ecological hierarchies shaken. The great biodiversity that had flourished during the warm, shallow seas was largely gone. But from the ashes of that collapse, something resilient and inventive arose. Recovery was not an instant, tidy process. It was messy, regional, and staggered. In some shallow basins, life returned slowly, with the same survivors that had weathered the storm, while in other places, entirely new assemblages formed from descendants that had found refuge in deeper, more stable waters. The first waters to refill were nutrient-rich, heavy with sediments washed from the newly exposed shelves and newly erodible continents. This flush of minerals triggered massive plankton blooms in sheltered bays and continental lagoons. Where dead plankton sank and decayed, oxygen levels could drop locally, but where currents mixed the water, oxygenated zones expanded, allowing new communities to establish. These early bloom and bust cycles favored opportunistic species, fast reproducing filter feeders, small motile grazers, and any organisms that could quickly exploit abundant but unstable food supplies. Some brachiopod lineages that had nearly disappeared in the late Ordovician found new ways to thrive. They diversified into novel shell forms and modes of life. Some reclined within the sediment, others anchored to cobbles and shell beds. Bryozoans, with their colonial lifestyles, radiated again, building delicate structures that provided shelter to tiny juveniles and microfauna. Crinoids returned more robust than before, their stalks and feeding arms forming meadows where juvenile organisms could hide. In ecological terms, the Silurian recovery was a story of smaller bodies, faster life cycles, and a shift toward modular and colonial strategies, life experimenting with cooperative architectures that reduced individual vulnerability. Predators re-emerged, but they were often different in strategy. Where giant nautiloids had prowled before, the Silurian saw a rise in more agile, faster hunters. Cephalopods continued, but with modifications. Curved shells for tighter maneuvering, lighter chambers for faster neutrally buoyant travel, and more compact forms that could dart through reef frameworks. Arthropods, especially eurypterids, the sea scorpions, diversified into new predatory roles. Some eurypterids grew larger in sheltered carbonate platforms, while others specialized in shallow, brackish waters where rapid growth and a high tolerance for variable salinity proved advantageous. And the vertebrate story continued, quietly but inexorably. Jawless fishes diversified into an array of armored forms, better adapted to grazing near the substrate, to filter feeding in currents, and to ambush tactics. Sensory systems refined, electroreception, and more sensitive lateral line systems helped fish detect prey in murky, sediment-laden waters. By the end of the Silurian, these early vertebrates had laid down anatomical blueprints that would, over hundreds of millions of years, lead to jaws and the incredible diversification of gnathostomes, jawed fishes. But perhaps the most profound thread of this recovery was not merely who survived or returned, but the way ecosystems reorganized around new physical realities. Exposed shelves became peatlands and emergent flats. Wave-dominated coastlines, carved and smoothed by erosion, generated an array of niches. Tidal flats alternated with lagoons. Saline marshes arose. River mouths carried sediments and nutrients inland. These dynamic transitional zones were crucibles for evolutionary innovation. They favored organisms that could tolerate change, Euryhalan species, opportunistic colonizers, and modular builders that could repair damage and regrow. In these mixed environments, the chemistry of the water began to change in another direction. Alkalinity rose in some basins, favoring the precipitation of carbonate platforms and the formation of true reefs once again. But the architects of Silurian reefs were not necessarily the same builders as in the Ordovician. Instead of the earlier assemblages, reef frameworks became increasingly the domain of coralline and stromatoporoid organisms. Massive sponge-like builders whose skeletons could form sturdy mounds. These new reefal structures promoted verticality in ecosystems, creating shelves and overhangs where juvenile organisms could feed in surface currents, while protected by the reef structure below. Reef ecosystems, more robust and resilient than before, became hotspots of innovation. They hosted specialized niches for grazers, filter feeders, and micropredators. Another profound development of the Silurian recovery was the increasing complexity of food webs. Trophic levels thickened as secondary consumers gained energy from increasingly abundant primary producers. As energy moved upward more efficiently, selection favored innovations in locomotion, sensory perception, and feeding mechanics. Muscles could be more complex because mitochondria supplied the needed energy. Nervous systems could support faster reflexes. Mouthparts diversified into scraping, suction, and grasping designs. Animal interactions were no longer simple predator-consumer acts, but complex chains of influence. A feeding strategy by one species altered sediment dynamics, which in turn affected algal growth, which then influenced the distribution of filter feeders. The Silurian biosphere developed feedback loops that were ecological rather than chemical, and these loops made local habitats more self-stabilizing. One of the silent revolutions of this time was in the microbial world. Bacterial mats and biofilms continued to influence sediment dynamics, but now they interacted with eukaryotic grazers in new ways. The grazing pressure from small invertebrates suppressed some mat formations, but encouraged the growth of other microbial communities that were less vulnerable to grazing. Some bacteria formed biofilms that trapped fine sediments, stabilizing muds and enabling colonization by juvenile organisms. Microbial communities became architects of microhabitats, creating islands of oxygenated space in a largely heterogeneous seafloor. These microbial eukaryote interactions were fundamental to later transitions onto land. They prepared substrates that terrestrial plants could use millions of years later. And then there was the quietly unfolding move toward land. Life on land during the Ordovician-Silurian transition was still microscopic, but the steps toward macroscopic terrestrial life were being taken. Algae and cyanobacteria established mats along riverbanks and tidal margins, creating thin films of organic matter that kept sediments damp and trapped fine particles. These mats began the slow process of soil formation, the earliest pedogenesis. Small, lichen-like partnerships between fungal-like organisms and photosynthetic microbes initiated nutrient cycles that would eventually support non-microscopic plant bodies. The first true vascular plants were still tens of millions of years away, but the ecological scaffolding, soil chemistry, biofilm stabilization, nutrient retention was being constructed. In sheltered estuaries and the mouths of rivers, larger organisms found new ecological opportunities. Brackish waters with their fluctuating salinity and rich nutrient loads selected for tolerance. Some eurypterids evolved to brave low salinity habitats, prefiguring later groups that would fully colonize freshwaters and ultimately land. These transitional habitats were evolutionary bridges, places where the descendants of marine organisms would gradually gain the adaptations necessary to live away from the open sea. On a physiological level, several trends converged to make future terrestrial life possible. Respiratory systems became more efficient. Cuticle-like protective layers evolved in arthropods to reduce water loss. Sensory systems adapted to detect cues in air as much as in water. Reproductive strategies shifted as well. Where broadcast spawning in the open ocean had been the norm, more protected brooding and egg-carrying strategies appeared, setting the stage for life cycles that would tolerate desiccation and terrestrial exposure. Geology and climate continued to interact with biology in complex ways. The breakup of continents and the transgression-regression cycles that followed produced repeated opportunities for dispersal, isolation, and adaptive radiation. Isolated basins served as evolutionary laboratories where lineages could diverge under differing ecological pressures. When sea levels rose, relic populations would be reconnected, mixing previously isolated gene pools and provoking bursts of speciation. The timing of glacial pulses and their retreats therefore played a decisive role in the tempo of biological innovation. Fossil records from this interval reveal the fingerprints of these ecological shifts. Lagerstätten, exceptional fossil deposits, capture moments when ecosystems were preserved in exquisite detail. Crinoid beds, articulated trilobite clusters, and dense brachiopod assemblages that show life in ecological snapshots. Growth rings, shell morphologies, and isotopic signatures record aspects of the chemical environment, enabling paleobiologists to reconstruct salinity, temperature, and nutrient trends. When these proxies are woven together, a picture emerges of a dynamic, often precarious biosphere that alternated between boom and bust, catastrophe and opportunity. And yet, with all the upheaval, one idea remains constant. Life invests in redundancy and modularity when the environment is unstable. Colonial life, multicellular cooperation, and flexible life cycles dominate the recovery because they spread risk across many units. A modular bryozoan colony can lose part of itself to a storm and regrow. A brooding arthropod can protect offspring during a short-lived harsh phase. These strategies resonate through time. They become recurring themes in Earth's evolutionary playbook. By the late Silurian, roughly 40 to 50 million years after the Ordovician collapse, ecosystems had stabilized in new configurations. Reef frameworks were robust. Vertebrate lineages had diversified further. Arthropods had explored brackish and marginal habitats, and the earliest meadows of multicellular algae dotted the shallow coasts. The stage was set for even more radical innovations that would define later geological periods: the explosion of fish diversity, the establishment of terrestrial flora and fauna, and ultimately, the colonization of land in force. But none of these later events would have been possible without the particular combination of catastrophe and opportunity that marked the Ordovician-Silurian transition. The extinction removed entrenched incumbents and opened vacant ecological space. The glaciers reset coastlines and produced nutrient pulses that drove opportunistic radiations. The survivors that adapted to the new chemistry and climate seeded the future. Evolution is not a ladder but a branching process. Mass extinction prunes enormous swaths of branches but leaves root systems intact. From those roots, the forest regrows differently. In the grand sweep of deep time, the Ordovician and Silurian together illustrate a fundamental truth. Earth and life are a single, co-evolving system. A change in climate begets new niches which beget new forms. The planet's rocks store the memory of these changes, but the living record is carried forward in genes, ecologies, and innovative life strategies. The story is cyclical and cumulative. Catastrophe yields novelty. Novelty yields complexity. Complexity yields both robustness and fragility creates the conditions for the next major transformation. So when we look at a world of reefs and fishes and reef predators, When we see layered sedimentary deposits that preserve the contours of ancient coastlines, when we study the microstructure of shells and the isotopic ratios trapped in ancient seashells, we are not just seeing dead things. We are reading the record of a planet that has repeatedly tested life's limits and repeatedly reshaped not only the living forms that bent to that pressure, but also the very stage upon which life performs. The Ordovician's collapse and the Silurian's slow rebirth remind us that the history of life is not a straightforward march toward complexity, but a complex dance of destruction and renewal, improvisation and repetition, loss and creative reorganization.